Thank you, Liam. And it's great to be live in the flesh behind a podium, actually, as opposed to sitting in my home office. This is exciting to be opening up this meeting, and it's nice to be actually going ahead of Mitch for once. That way, won't be so rushed for time. But um, so I'm transitioning into a new role as the NESDIS fire lead. We're trying to consolidate, organize, and uh, um, integrate the various wildland fire activities going on across all of the NESDIS offices and coordinate that, strategize that with all of the NOAA line offices that work in this space, as well as all of our external partners. And the demand, regards that, we all know this is a big problem, and the demand for actionable information and analysis-ready data for wildland fire applications has never been greater. Its demand is really high, and it's increasing. So in response to that, in NESDIS, we've been working on a plan to transform our fire products and services portfolio to meet this challenge. And so in this talk, I'll discuss a little bit about our overall transformation philosophy, rationale, strategy, and highlight some early progress in doing that. And so you may say, why is this at this meeting? Well, I think wildland fire is a really ideal application for illustrating the value of low latency data that is rapidly transformed into actionable information. And I think some of the concepts in here, a lot of the concepts in here will translate beyond the fire thematic and other areas where such things are important. Okay, so first, our overall philosophy in this endeavor. And consistent with the modern day innovators, we want to start with the customer experience, or you could think of that as in terms of starting with impacts. What impacts do you want to achieve? So Steve Forbes is famous for saying you've got to start with the customer experience and work back towards the technology, not the other way around. I think in our community we do a lot of, we have these products, how can we factor them into your application area or different application areas? So here's a product, how can it help you? And you always need to do some of that. It's not right or wrong, it's just how much of that do you do relative to with starting a focus on tasks users are trying to accomplish, and then go into the solution space and figure out where you need to go there. And with the fire transformation, the fire product and services portfolio transformation, we're trying to start with a real focus on what users are trying to accomplish and then build the solutions around that, as opposed to taking existing solutions and forcing them into work for this challenge, which we know isn't going to work for this particular problem, at least. So just to sort of give a specific example between a sort of a more of a product and algorithm mindset versus an impact mindset. So I think it's pretty common to start with a product-centric focus, where you'd say, hey, I have an idea for developing a new or approved algorithm or product, and my goal might be, if we're doing fire here, is to develop an algorithm for satellite-based fire detection, which is totally reasonable. But if you sort of turn this around and look at it from an impact-centric focus, you may be doing more generally, you want to develop and deliver timely, accurate, and actionable information. And going back to the fire example, your goal that would correspond to the goal in the product-centric would be to improve the timeliness of the response to a new fire ignition. So these are very different mindsets. So by taking a really challenging use case, such as improving the timeliness of the response to a new fire ignition, you identify the most challenging requirements that an algorithm has to address, and you also identify the most challenging features that have to be built into your algorithm. And most of these things wouldn't be identified if you were starting in a very generic sense. Hey, I want to develop a generic fire detection algorithm, and then I'm sure it'll be useful for all these applications after the fact. So for instance, if you're developing, history says, if you're starting with developing a generic fire detection algorithm, you're not worried about event-based feature detection or tracking in time. And those things would be absolutely essential for improving the timeliness of response to a new fire ignition, because you would have to do alerting. You would have to push that information out to users, not just have it in an algorithm. And in order to do that, you have to know what features you've already detected. It may also influence what your detection goals are. So the upper limit of detection sensitivity in satellite data is human expert analysis. And so in the most challenging use case, that's what you want to approach. The impact-centric focus also makes you realize that beyond science algorithm development, there's a whole bunch of things that has to happen. You have to focus on user interfaces, dissemination, access, all of those things. If the data is just sitting in a file somewhere, it's not actionable. So the way we sort of conceptualize how we work is we have this, this service delivery framework that was recently defined by the NOAA Weather, Water, and Climate Board. And it consists of 7 elements that underpin continuous engagement with users. And the 7 elements are: 1, build relationships with end users. Once you've built those relationships, gather and really understand their needs, and then you have to translate them into the space that you work. And then you have to assess those needs. Okay, is this aligned with what we can provide? Is it aligned with our priorities? There are limited resources. You have to assess that. Do we have solutions that already may address this? Then you go to addressing the need. That's sort of what we would think of as algorithm development, and then deliver it. Get it out there. Make sure it's you know, you're reaching the last mile, and then you have to continuously evaluate how you did. So in terms of FIRE, what we're looking to deliver is actionable information and analysis-ready data. And when I say analysis-ready data, it's just an acknowledgement that you're not always delivering to a human. Sometimes you're delivering to another system, like a data assimilation system. But you want it to be analysis-ready and appropriate, fit for purpose in those. So the rest of this talk will be structured around these different elements in this sort of service delivery framework. So first, build. Fortunately, NOAA, we have a good start on this because NOAA is a longtime partner at many levels, the national, the regional, and local for FIRE. So we have a lot of existing relationships that we continue to support, and there's new relationships being added all of the time. So the build part, we had a really good start on. Gather, so identifying the critical gaps. We've relied a lot on high-level government reports, such as this report from the Department of Homeland Security and FEMA, also the National Wildfire Coordinating Group, and as you'll hear, I think more from Kat later, is the GeoXO program has really been out in front in terms of reshaping how NESDIS does user engagement. They've held a series of thematic workshops, including one on fire. They've hosted tabletops that are thematically focused, including one on fire recently. And then there's a lot of just sort of organic or well-organized outreach and engagement going on. And we're also leveraging what's going on in other agencies. NASA has had a series of workshops recently dedicated to fire that we're certainly participate in and are leveraging. Then you have to translate and assess. So we want to have a framework for this, a sort of problem-centric framework for this. And so we have this, what we call the FIRE problem lifecycle wheel that covers the pre, active, and post-fire phases of the problem. And this wheel was developed by the NOAA Forest team, which is the fire observations and research team. It includes all the NOAA line offices that work on fire. So this is the conceptual framework that we build around. And so what I'm highlighting on here are some of the, at least at a high level, the activities that are high priority for NESDIS, where NESDIS has the leading role. We're doing these collaboratively, but this is where NESDIS has a leading role. So starting with detection, we want to fully utilize GOES and JPSS for timely detection and notification of new fires. One thing to recognize is that the GOES-R and JPSS satellites are even more capable than we expected them to be in this realm for this application. They can detect fires earlier than we were expecting them to be able to, and we really need to take a full advantage of that. And this is actually, we have our sponsors who are looking at this and looking at NOAA to do this as well. This is just a tweet from a White House statement that went out last year calling out the importance of NOAA in the realm of fire detection. Then you have forecasting. So this is sort of optimizing the satellite-derived information for fire behavior and smoke forecasting. We really want to build upon the success that we've had getting satellite-derived information into smoke forecasting models and really be able to support the next generation of those models. Fire behavior forecasting is a big need, and there is no operational capability for that right now, but there is a huge demand for it, and the observational constraints that satellite provide play a big role, but we need to make sure the satellite are really fit for that purpose. There's also a lot of opportunity in this space to extract prognostic value from the satellite data itself. If you're monitoring fire intensity over time and the trends in that intensity over time, that gives you some nowcasting information that can be exploited possibly with artificial intelligence and through fusion with other data sources. We also have to be concerned with having robust satellite-based long-term data sets so that we can understand trends and patterns in fire behavior. And also develop fire weather forecasting and analysis capabilities that are better so that we can actually assess threat potential. That's, again, another huge demand is, okay, where should a fire ignite is the threat the greatest? And then, of course, all of this is no good unless you really make sure that what you're producing is accessible, interoperable, and usable. That's not the sort of exciting part from a science standpoint, but it's absolutely essential. So assess. So just looking at the current NESDIS fire products and services portfolio here. So we have the GOES-R products that come out of the GOES-R ground segment. We have the JPSS I-band fire detection that comes out of the NOAA central operations within what we call the NDE system, as well as in CSPP. There's an enterprise algorithm that will be used to generate some the fire products from non-NOAA satellites such as Meteosat second generation, and that will actually eventually be used to generate the JPSS products as well. And then we have some value-added things, such as the hazard mapping system from the Satellite Analysis Branch, and there's fire data and information from the National Center for Environmental Intelligence and NCEI. And so within this realm, there's been some really good success stories. You think of the JPSS products getting into the high-resolution rapid refresh model for forecasting smoke, and that was operationalized. That's a big success. The hazard mapping system is used by the environmental protection to give people localized insight into air quality. And there are other success stories, but when you look at this, it really does generally require some assembly on the user's part. It's kind of like a jigsaw puzzle. These are coming from different data streams, different sources. There's a lot of integration and a lot of application development that the user has to do. So they have to assemble this puzzle. And some users do that well. They can assemble the puzzle, it's good, their needs are met. Other users, they're either unable to assemble the puzzle, or they do, and it doesn't add up to the picture they were expecting because the product requirements were inconsistent with the needs. So this isn't that there is bad science here. The science here is excellent, but the requirements are not always, we're not set up for all of the applications, including some of these more challenging ones, such as early fire detection and near continuous monitoring of fire intensity. These algorithms also exist in rigid systems that are really reliable and secure, but not very agile. So it doesn't allow for a lot of rapid development and development of higher order capabilities on top of it. And then the accessibility and data formats and usability is, we know that we need to do better there, particularly for users that work in GIS-based systems. So with that in mind, the goal for addressing here, the ultimate goal is the development to transition from that sort of somewhat stovepiped approach to a more dedicated fire information system that can ingest single or multi-source GEO and LEO satellite data plus whatever supplemental data is needed. It's a single system dedicated to fire. So it's not fire plus a lot of other thematic area products. This would be a fire information system that is hosted in the cloud environment that NESDIS works in, calls the NESDIS Common Cloud Framework. It would connect to a NESDIS storefront dedicated to fire, but we recognize that a centralized storefront isn't the best solution for all users, especially those that have direct readout capabilities. So making sure that the software is available once it reaches a certain level of maturity is also really important. Okay, so now I just wanted, the last part here, I want to talk a little bit about some progress that we've made on actually addressing, delivering, and evaluating. And this was done under a fire pilot project that started a couple of years ago, and this fire pilot project is now transitioning into actual resourced projects to finish this job off. So we started with, in this pilot, we wanted to see if we could take something called the Volcanic Cloud Analysis Toolkit, or VOLCAT, which addresses a related issue, volcano monitoring, and it addresses it in this sort of problem life cycle way that we want to address fire. So we have like thermal monitoring, eruption alerting, tracking of volcanic features, characterization, supporting forecasting. So it's kind of analogous to what we want to do for fire at a very high level. So we wanted to see if we can take this software, which already had a lot of high-level capabilities, including event-based detection and tracking, things we would need to do to say, alert on fires, and see if we could quickly adopt it to fires. The other reason we wanted to look at doing this with VOLCAT is because the software practices that we're using are conducive to sharing of software and porting it around and getting it implemented on a variety of platforms. So we've already done a lot of work on containerization and automation, automated building and testing of those containers, and also testing within cloud environments. So we thought that was also a benefit. So just some early highlights from this. So one of the things that we did is we took a dashboard, a web-based dashboard that we had developed for alerting users to new volcanic events, and we repurposed it for fire ignitions, so new fire ignitions. So what this dashboard here on the left shows is each one of these bars is a new fire event that was detected by, in this case we're using GOES 16 and GOES 17, but you can use other satellite sensors. We're using 1-minute data and 5-minute data over the continental United States and Canada. And each of these colorized bars shows a new fire ignition event that was not previously detected by the system. If you didn't weed out or filter out things that were already detected, it would fill up and become completely unusable. And each color has meaning. It is associated with the fire weather conditions. So we want to tie this in, present this in a way that's really meaningful. So not only do you have a fire ignition, but is that fire likely to spread rapidly and become a problem? So the magenta color is associated with extreme fire weather conditions as defined by the Storm Prediction Center, NOAA's Storm Prediction Center. The red is critical fire weather conditions. There's an orange color that's not showing up on this one, but that's elevated fire weather conditions. The yellow is nominal fire weather conditions. And green means that the detection was co-located with a persistent anomaly source. Could be like a gas flare, something like that. And this dashboard updates automatically every 30 seconds, and then there are links from the dashboard to imagery and an alert report so that users can quickly assess whether or not the detection needs action or not. The dashboard is powered by an improved satellite fire detection algorithm that is sort of illustrated with this animation to the right. This is a GOES 17 animation over California, and it's centered on a new fire detection which became known as the NOAA fire. And in this particular case, so when the fire is detected, the red box appears around the feature. And in this case, the algorithm detected this fire as soon as it showed up in the imagery, the GOES 17 imagery. That's the goal, is to try to do what a human can do, but a human can't look at all of the imagery. And actually, in about 1 out of 10 cases, 1 out of 20 cases, it really depends, these detections from satellite come in ahead of the 911 calls by 10 minutes or so. And that's a big deal for the initial response. It's not going to happen every single time because there's other sources. There's cameras, there's people, and But if you can do it 1 out of 10, 1 out of 20 times, that's impactful. And just to highlight the value of low latency satellite data. So here's a detection in Santa Barbara County from GO17 1-minute data. And this alert was generated within 90 seconds of the last photons from this scan sector hitting the detector. Because it's being processed here at the University of Wisconsin. We're a GRB feed. This is 1-minute data, so it's a small scan area, so the turnaround time is very, very quick. So this is truly near real time, and minutes and seconds count here. The satellite detection that we're using is sensor agnostic. So the same algorithm that is applied to GOES-R is applied to JPSS, could be applied to HIMAWARI-8, could be applied to AVHRR, METOPS second generation when that's flying, etc. And it sort of automatically scales based on the spatial resolution of your data. So your detection sensitivity naturally ramps up as the spatial resolution of your sensor goes up. And in terms of the low latency data, LEO data play a big role in this as well. And excited to hear from Bruce Flynn later this week about the ultra low latency project that Liam's group is pursuing. Okay, so final highlight here. Not only is fire detection important, but fire intensity characterization via the fire radius power parameter. So what I'm going to play here is an animation. In the top is just multispectral imagery, false color imagery. In the center of the image, you're going to see the Bobcat fire from 2020. We're using this because we just happened to use it recently in a tabletop exercise. But you could do this with a variety of fire events. And in the bottom is a time series. And the red line is the fire radiative power in watts. And when it gets above about a gigawatt, which is 10 to the 9th on this scale, and especially as it approaches 10 to the 10, which is 10 gigawatts, you'll notice pyro-CB generation. So that's sort of the pyro-CB threshold is about 10 to the 10. So what this time series, which is updated every single minute, will do, it provides you minute-by-minute insight into the fire intensity, and it could do so even when clouds are present or thick smoke, because we can now correct for those things. Because when you're doing volcano remote sensing, that's really important because volcanoes are cloudy more often than not. The green line is the atmospheric transmittance. The lower the value, the more attenuation is going on in the atmosphere. So I'll play this. And you can see the start of the fire and the quick ramp up in the radiative power. And as it approaches that 10 gigawatt number, you'll notice in the imagery the formation of clouds around the fire. Those are pyro-CB. These are not the most intense pyro-CB that you'll see. But they are associated with extreme fire behavior, which is a major hazard to those working the incident. And to those in the path of the incident. And so, not only is this sort of a diagnostic tool, but you can imagine that this is something that you can plug into a more prognostic capability through the use of artificial intelligence, bringing in other data sources. These time series we want to integrate into a web-based tool, just like we did for volcano monitoring, where we use a Grafana-based dashboard to have interactive time series data. And we would want to do this for every major ongoing fire incident in the United States. Okay, just a quick look at the satellite data sources that we're using currently. That's in blue. Black is what we are planning on supporting. Okay, so the next step is to kick off get out of this pilot stage and really kick off the more formal projects. These projects we're able to do these because of support from the Disaster Relief Supplemental Act and the Infrastructure Investment and Jobs Act. So now we're putting together a big team of experts to really take this to the next level, expand the development, the testing, and the evaluation, and achieve operational readiness, at least for certain pieces of the system, within 2 years. The team is all of the players who work in this space. So this is not a competitive. This is NESDIS working as one on this. So we're not. We have all of the people working on who've worked on the legacy products working on this and working together for this transformation, as well as some new partners that we've brought in, such as Wi-Fi out at the University of California, San Diego, to help us reach further down the value chain. Okay, last slide. So I was trying to figure out last night sort of how to sum this up or wrap this up, and this is what I came up with. So impactful service delivery for at least for time-sensitive applications, I think of it as a four-piece equation if you want to get at actionable and impactful information. You need a deep understanding of user needs. That includes continuous engagement, trust building, user readiness for what you're providing them. Of course, you need science. It may be physical science, it may be data science, or it may be both. You need low latency data, absolutely critical. You need robust software and interfaces and dissemination and software that is developed according to agile best practices. In my view, and especially for looking at this from a wildfire lens, if any one of those four pieces is missing, you take away any one of those, and you do not get at the actionable, impactful information. I think as a community, we tend to focus a lot on the second box, and other boxes sometimes less so. And all four of these need to be equally well addressed in order to meet this goal. And I'll just end with this, that in terms of direct readout sites, processing at direct readout sites has to be part of the equation if you really want to realize the full potential of satellite assets. It's for time-sensitive matters like this, an extra 5 minutes is a big deal. So I'll end with that thought, and we might have time for a couple questions. Thanks.
Thanks, Mike. That was very interesting. And sometimes when we get down in the weeds of looking at algorithms and software, we maybe miss the bigger picture. So glad to hear that you're focused on the bigger picture. So we have time for a couple of questions for Mike from the audience. No questions? Okay, Mitch.
Tell us more about the customer experience, because I think Steve Jobs was thinking like a customer, because in the early days, the customers weren't even thinking about iPhones and iPads. So I think part of the equation is to really, even though you might be the producer or developer, you have to think like a customer in order to be successful.
Yeah, I agree with that. I absolutely agree. I think you have to be a user of your own products, and you have to think about it that way. Yeah, I can't disagree with that at all. I think that is an important element.
So just to follow up on that comment, I think I also read at one point Steve Jobs said, the customers will know what we want, what they want, when we tell them what we have. So maybe there's like a virtuous circle.
Yeah, I mean, but the underlying need was very stable. So think of the iPhone. What is the underlying need? People need to communicate. Right? In the 1800s, you used to walk next door to communicate to your neighbor. Then in the 20th century, you might call them on a landline. Now you just might text them. The underlying need, the technology for addressing that need has changed drastically, but the underlying need, the need to communicate, has remained stable. And so I think what he understood and other innovators understood is that, these underlying needs that people take for granted.
Yes, Marie.
Yeah, so there's a lot of things I've learned being in the private sector for the last 10 years that I really did not appreciate before. And so just as we have very scientific specific terminology, we say here that customer and user are not equivalent. And it's really important that when you think about customer, there's an element of the willingness to pay in the customer. And that's always a really kind of a critical question to ask. That doesn't necessarily mean like a commercial product that we pay for, but like who's going to, and when you find out what they really are willing to pay for in some fashion, then you'll find out what their real requirements are. And I think we do that as consumers. But I would be careful about customer versus user. Now, with these last two, and now when I look at your diagram here, the last 10 years have seen such massive changes in what's happening in cloud-based architectures and solutions that are really driving down latency and software development. So my actual question is, if you thought of your final service going out being on the cloud directly so that all your fire responders could be using their phones or whatever, how is it, and maybe at some point there's a transition there to maybe private sector or different other partners, how would that change your thinking about the development?
Yeah, I mean, I think we do think about that. In NOAA, we do tend to use user experience, not a customer experience, but that wasn't convenient for the Steve Jobs quote. But yeah, I mean, we are thinking a lot about intermediaries in terms of, we can't reach every user down the value chain. There are ways to do that. And private sector, commercial sector is one mechanism for doing that. And so, one of the things, the lowest hanging fruit is just to make sure that we're providing data in accessible, discoverable ways, in formats that are interoperable with a variety of platforms and applications. And then that will allow us to reach the most people, including through commercial applications.